Hello. In this video, we will cover section 5.3, which is on conditional probability. Conditional probability is calculated based on the condition that a criteria or action is met. For example, what is the probability that a person makes $100,000 per year, given that they have a college education? Or what is the probability that an ace is drawn from a deck of cards, given that an ace has already been drawn from the deck? Let's look at an example to try and illustrate this. Find the probability that a college-educated person is married using the following table. This can be translated into find the probability that a person is married given that they are college-educated. Sometimes you see the different phrasing here. And so if you do see this initial phrasing, so find the probability that a blank is blank, then the thing that the first thing is the condition. So you're being told that a person is college educated and you're being asked to determine, are they married? All right. So if you don't have a strict given that in the phrasing, then look for this alternate phrasing where it goes through and it says, find the probability that a blank is blank. The first thing is going to be the condition. And then the second thing is what you're trying to find the probability of. Okay, moving on. The rephrasing is important because we need to be able to identify the condition. Yes, that's critical. In this case, being college educated. Once we identify the condition, we can go through and find the probability. All right, so once we have the condition, we find the probability by restricting the table to only the parts that meet the condition. All right, so we're told the person is college educated, and we want to know, are they married? So if we know that the person is college educated, then we don't care about the people who have less than high school or high school education. We only care about the people who are college educated. So we just highlight that column and ignore the rest of the table. And then from there, to go through and find the probability, we'd use the exact same method that we did in the previous section, which is we look at the number of people who meet the criteria over the total number. All right, and so in this case, we're being asked to find the probability that someone who is college educated is married. All right, so that's going to be there's 98 people who are married, and there are 143 who are college educated, and so that's our probability. Note that compound probability with and is not the same thing as conditional probability. All right, let's go through and check this because this is something that people frequently get confused on, is they want to go through and find the probability that a person is college educated and married, and they think that's the same. All right, so if we recall the way that we do that, we look for the place where these two overlap. So college educated and married, that's going to be the 98 here. And then the denominator here is then out of the total. We haven't gone through and just done a restriction with the, without the given that part, without the condition. We haven't restricted this to just college educated people. And so we're going to have 98 over everyone that's in the table over 665. And so that's the difference. That is not the same as 98 over 143. Okay, so you cannot go through and just replace conditional probability with compound probability from the last section. All right, so here are some equivalencies just for notational purposes, and we've already kind of covered this first one. So the probability that a college-educated person is married is equivalent to saying the probability that a person is married given that they are college-educated. So that's what we just discussed. If you're asked to find the probability that a blank is blank, the first thing is the condition there, and the second thing is what you're trying to find the probability of. And the cleaner phrasing, at least in terms of conditions, is we're trying to find the probability that a person is married, and then given that the person is college educated. I like the second phrasing better. It's easier to identify what the condition is there. It's very clear that what's after the given that is the condition. And then in notationally, this is the way that we're gonna go through and represent this. We'll still do the probability, P, we still do the parentheses, and then within here, we go through and we put the two events with a line, and the line here you can translate as given then. So in this case, we would say the person is married given that the person is college educated. So we put the condition second, and then the thing we're finding the probability of first. Okay, so if we were to go through and look at this first thing here, if this was event A and this was event B, all right, then it would go probability of B given A. That's the order, okay? All right, let's look at a homework example. A person is selected randomly from the group whose responses are summarized in the table. Find the probability that the person was female, given that the person said yes. find the probability that a person who was unsure was female, and then find the probability that the person was female and said she was unsure. Okay, let's just kind of go through that quickly before we look to the solution on the next page. So find the probability the person was female, given that the person said yes. So we were told that the condition here is that the person said yes, so we want to restrict the table to just that part. We want to ignore the rest. So we start off by just looking at just the yes. So that's just this column here. That's the only part that we care about. And then when we want to go through and find the probability that the person was female. All right, so female, so we've got 587 female over the total for that row. Sorry, did I say column earlier? Row is 997. So we'd have 587 and 997. Now this time, find the probability that the person who was unsure was female. So this is that alternate phrasing where they don't use given that. So this is the person who is unsure. That's our condition, and we're finding the probability that they were female. So that's saying to go through, take the unsure column here, and then we take the female, which is 81, and put it over total, which is 167. And then finally, just to go through and drive this point home with the and, if we want to find the probability that the person was female and she said she was unsure, okay, then to do that, we look through the table, we find female, unsure, there's 81 of those, and it's 81 over the total from the entire table now, 1254, okay? All right, so let's just recap. So find the probability that a person was female, given that the person said yes. So female, given yes, we take yes, 587 female, 997 total. Find the probability the person who was unsure was female. So now we've got unsure as the condition, and we're finding female. So we take unsure, that's this row, and then we take the number of females over the total number for the row. And then finally, female and unsure. So we look for overlap of female and unsure. There's 81 of those out of the total for the entire table, which is 1254. So no condition, no restriction. You take the entire table for the total for the sample space, if you will. So you got event space over sample space, to use the language from the last section. All right, so while conditional probability is not the same as compound probability with and, a formula does exist that connects the two. All right, and here is the formula. So you've got the probability of A given B is equal to the probability of A and B over the probability of B. Okay, so you've got to go through and connect these two. You need to divide by the probability of B. If you do that, then the two are equal. So one of the cool things you can do is you can actually rewrite this formula into this alternate form where you get the probability of A and B by itself by moving the probability of B over to the other side. We're going to revisit that formula later in the PowerPoint because this formula actually ends up being really useful. But first, let's talk about independent versus dependent or associated events. Two events are independent if one event occurring does not affect the probability of the other event occurring. So if you were to think about rolling a dice twice, if you pick up a dice and you roll it, and you pick it up and roll it a second time, the second dice roll is not affected by the result from the first dice roll, right? It's not like you roll a dice and you get a 6, and then when you roll it a second time, then the probabilities change. No, the possible results and the probability of them stays the same independently from dice roll to dice roll. The same thing is true of flipping a coin. If you were to flip a coin multiple times, each time you flip the coin, you hit the reset button. The previous results do not change or affect the results of future coin flips. And then to use something that's non-action oriented, because we can have events that are non-action oriented. If someone were to say, how about having a college degree and having brown eyes? Are those related? Or do you think of those two events where one affects the other? That if you have a college degree, then you are more likely to have brown eyes. Or if you have brown eyes, then you are more likely to have a college degree. No, those two things are completely unrelated. There's no connection between them. If you have brown eyes, there's no connection there. You're not more likely to get a college degree because of it. Meanwhile, so two events are associated or dependent if one event occurring does affect the probability of the other event occurring. All right, so associated is the main term we use, actually, the second of the two up above. That's the more common one. That's the one you're going to see in the homework. All right, so two events are associated if the outcomes do affect each other. All right, so if you pull two cards from a deck, now the issue there, if you're like, wait, isn't that the same thing as rolling a dice twice? No, see, when you pull the first card from the deck, then the next card pull, the probability is going to be affected. All right. So if you go through and you pull an ace from a deck, there originally were 4 aces in the deck, and now there are only 3. Okay. So there is less of a chance of pulling an ace on the next card pull because you've already pulled 1. All right. So that's what we mean by associated or dependent. The events affect each other. Same thing goes for marbles from a bowl. So assuming you pull them and you don't put them back in. Okay, so there is something called replacement. If you have, whether it's cards or marbles, if you go through and do a card pull with replacement, then they events become independent. But as long as you don't replace the card back in the deck or replace the marble back in the bowl, all right, if you pull a marble from a bowl, then what's left in the bowl is going to be different from when you first pull the marble. All right, so the outcome is going to affect the next marble pull or the next. Is it pull? Next take from the bowl, and you understand what I mean. And then finally, having a college degree and your income level. So those two things are associated, or they are dependent upon each other. If you have a college degree, then your income level is affected by that. You're more likely to have a higher income level because of the fact that you have a college degree. All right, and so using that, using independent versus associated, we can actually go through and define some and probability rules. So in the last section, we went through and defined or probability rules. We couldn't do it in that section, but we can go through and in this section, we can define and probability rules. If event A and event B are associated, okay, meaning that the outcome of one affects the outcome of the other, the probability of event A and event B is the probability of event A multiplied by the probability of event A given event B. Okay. I think actually that's supposed to be the opposite. The probability of event A multiplied by the probability of event B given A. Yeah, this is supposed to be reversed. Okay, you can see it in the symbols. I did write it correctly. If event A and event B are independent, then the probability of event A and event B is the probability of event A multiplied by the probability of event B. All right, so we don't have that conditional part. All right, so those are the two different cases. So if you have associated, then you need to go through and adjust for so it makes sense here. If you think about associated, if associated means that the events affect each other, then when you go through and find the probability of the two events occurring, then if you take the first one, it happens, and then you need to multiply by the probability of the second one, given that the first has already happened. So since associated events affect each other, we need to go through and adjust the probability for the event for the fact that the first one has already happened. Meanwhile, if the events are independent, we don't need that adjustment, right? If event A does not affect event B, then we can go through and just multiply by the probability of each. All right, so let's look at some examples. All right, so a dice is rolled twice. What is the probability of rolling an even and rolling a 5? And then what's the probability of rolling greater than 4 twice? All right, so dice rolls are independent. One roll of the dice does not affect the other. So we could find the probability by using the second rule, right? By multiplying the probability of the individual events. So the probability of getting an even and a 5 on 2 dice rolls is the probability of getting an even times the probability of getting a 5, right? So even is 3 out of 6, 5 is 1 out of 6. We get 3 out of 36 or 1 out of 12. And we want to find the probability of getting greater than 4 and greater than 4 on our 2 dice rolls, right? So we can find that by finding the probability of getting greater than 4 times the probability of getting greater than 4. So greater than 4, that means 5 or 6. So that's 2 possibilities out of 6 total. And then we do that twice. And so 2 6 times 6, 2 6, that's 1/9. Let's look at another example. Let's say a coin is flipped 3 times. What is the probability of getting all tails? What's the probability of getting heads, then tails twice? All right, so again, coin flips are independent. You can find the probability by multiplying the probability of the individual events. So if we want to find the probability of tails and tails and tails, then we can find that by multiplying probability of tails times probability of tails times probability of tails. So each time it's 1/2. So we get 1/2 times 1/2 times 1/2, which is 1/8. What's the probability of getting heads and then tails and then tails? So heads, then you can do that by multiplying the individual probabilities. So we get probability of heads times probability of tails times probability of tails. That gets us 1/2, 1/2, 1/2, which is 1/8. Again, you're doing it this way because the events are independent. When they're independent, you can multiply by the probability of individual events. All right, now we're going to get into associated events. How does it? It's going to be a little different. So 2 cards are pulled from a deck. What's the probability of getting 2 aces? What's the probability of getting an ace and then a non-ace? All right, so since card pulls are associated, right? So when a card is taken from the deck, it changes the deck. We can find the probability by using the first rule. That's the first rule for AND, which is we find the probability of the first event, and then we multiply it by the probability of the second event, given that the first event has already happened. So if we've got ace and ace, we'll go ahead and find the probability of drawing an ace multiplied by the probability of drawing an ace, given that an ace has already been drawn. All right, so the first one, the probability of drawing an ace. So this is all just the same technique that we used in the last video, in the last section. We go through and we use how many are in the event space that we're describing versus how many total. So how many aces are there? There are 4. How many total cards are there in the deck? There are 52. So that's the first one. And then we want to multiply by the probability of drawing an ace, given that an ace has already been drawn. So we need to think about how the deck would be different. So if you took an ace out, that means there's only 3 left. So for the second pull, we'd only have 3 aces left. And if you pulled an ace from the deck, there'd be 1 fewer total cards, right? So there's 3 aces left after you pull 1, and there's 51 total cards left now. And then you can go through and just multiply this across to get the probability. All right, let's look at another one. Now we've got the probability of an ace and a non-ace. The idea is you pull an ace, and then you need to multiply by the probability that you draw a non-ace afterwards. So again, ace, we've already gone over that. That's 4 out of 52. And then what's the probability of drawing something that's not an ace after you've already drawn an ace? So how many non-aces are there going to be left after you've pulled an ace? Well, there's going to be 48 non-aces left. Okay, originally there were 4 aces and 48 non-aces. You pulled one of the aces out, but you didn't pull any of the non-aces. So there are 48 non-aces left, and there are 51 total cards after you've taken 1, because they're started with 52. And then so we go ahead and multiply those 2 things to get the probability. And we went ahead and done that, and you get 16 over 221. Okay, and then one more. We got the marbles. All right, so covering all the bases here. A bowl contains 5 red marbles, 4 green marbles, and 3 pink marbles. 2 marbles are taken from the bowl. Oops, supposed to be from the bowl. Typo there. What is the probability of getting 2 red marbles? And what's the probability of getting a red marble and a pink marble? Since marbles taken from a bowl are associated, right? So when you pull a marble from the bowl, it changes the contents of the bowl. So since it changes the contents of the bowl, it affects the probability for future marbles that are taken from the bowl. And so then that means that we need to use the first rule, the one with the conditional probability. So the probability of red and red, so you need to find the probability of red and then multiply by the probability of red, given that a red has already been taken. All right, so for the first one, to find the probability of red, we go through how many red marbles are there? There's 5. How many total marbles are there? There's 12. And then we need to multiply by the probability of drawing another red. Well, if you've taken one of the 5 red marbles, there's only 4 left. And if you've taken a marble, you started with 12, so there's only 11 left. And so that's going to be the probability of drawing a red, given that you've already drawn a red. And then you just multiply it by multiply across to get this result, 5 over 33. All right, how about the probability of drawing a red and a pink? So we do the probability of drawing a red, and then the probability of drawing a pink, given that red has already been drawn. So red we've already covered, that's 5 out of 12. And then we want to multiply by the number of pink marbles, so there's 3. And then there's only 11 marbles left after we've taken 1 from the bowl. And so we get 3 over 11. So again, event space over sample space. Nothing new here. We're just adding this conditional stuff. And then multiply across to get your result. Okay, so we can go through and define at least probability by using the complement. So in the last section, we introduced the idea of the complement. The complement of event can be thought of as the opposite of the event. So if event A is to roll a 6, then the complement of A is to not roll a 6, which means to roll a 1, 2, 3, 4, or 5. And in symbols, we went through and described this. The probability of A complement equals 1 minus the probability of A. At least probability is the probability that an outcome occurs at least once when performing an event multiple times. So, for example, that would be the probability of rolling at least 1 6 when rolling a dice 3 times. So that's an at least probability. So you see these occasionally where you get this at least terminology, and that's what that means. I mean, it is just English too, if you just think about it. So what does at least mean? So here's the issue though. The complement of at least once is none. Those are opposites if you think about them, right? So if you don't have at least one, then you have none. As a result, we can go through and find the probability of at least once by using the probability of none, by using our complement definition here, right? So if these two are complements, then the probability of one complement equals 1 minus the probability of the other, right? If these are opposites, we can go through and just put at least once here and put none here, and we get a formula, okay? And then let's look at some examples. All right, so first example, roll a dice 3 times. What is the probability of rolling at least 1 6? All right, so the sample space for rolling 3 dice is, so if you wanted to do this the old-fashioned way, right, where you just wanted to go through and count up how many cases have at least 1 6, you'd have to write out all of the sample space, and there's 216 outcomes when you roll a dice 3 times. Right, and it would be a pain in the neck to go through and write out all 216 possibilities and then count how many of them had at least 1 6. So it's much easier to go through and use the complement, right? So what we've done is I've gone through and written the formula here. So we could find the probability of at least 1 6 by going through and finding the probability of 1 minus, by going through and finding 1 minus the probability of no 6s. Those are the opposites, at least 1 versus none. All right, the probability of no 6s is easier to calculate. The reason is that it can be represented by not getting a 6 on a single roll 3 times, which is easy to go through and calculate. Okay, those are the same. If you think about it, probability of no 6s, that means you roll a dice 3 times and none of them have 6s on them. All right, so you can go through and find not getting a 6 on a single roll 3 times. All right, and that's easy to calculate because the dice rolls are independent. This is not the case if you want to try and flip it around and say, okay, well, why don't I just do that the other way? Why don't I just go through and find the probability of at least 1 6 3 times and multiply those together? At least 1 6 when rolling 3 times is not the same as at least 1 6 on 3 separate rolls. Those are not the same. So no 6s is the same as not rolling a 6 on 3 single rolls. At least 1 6 on 3 rolls is not the same as at least 1 6 on 3 separate rolls. You can think about that, but that is true. All right, so if we want to go through and find the probability of at least 1 6 on 3 rolls, we can go through and use the complement, which is 1 minus the probability of no 6s on 3 rolls. And then we can rewrite that as 1 minus the probability of no 6 on 1 roll times no 6 on 1 roll times no 6 on 1 roll. And then that's 1 minus, and then the probability of not getting a 6, well, there's 5 ways to not get a 6 out of 6 total. So that's 5 6, 5 6, and 5 6. Multiply that all out, and you get 91 over 216. So that is a much faster way to go through and calculate at least probabilities, is to go through and use the complement. Much better than listing out the 216 possibilities. This took 30 seconds instead of a half hour. All right, so let's look at another example, which I'll try not to rush through. All right, so flip a coin 5 times. What is the probability of getting at least 1 heads? Okay, so we're going to go through and we're going to flip a coin 5 times. So you flip it, flip it, flip it, flip it, flip it, and then you want to know what is the chances that you get at least 1 heads on all of those results. All right, as soon as you see that at least language in there, you should be thinking, complement. I should use the complement here. Let's look at the answer. All right, so although not as large as the last example, the sample space for 5 coin flips actually is 32 outcomes. So it's faster and easier to go through and use the complement. So the probability of at least 1 heads equals 1 minus the probability of no heads. The probability of no heads over 5 coin flips is the same as the probability of not getting heads even 1 time on 5 individual coin flips. So we can go through and rewrite probability of at least 1 heads on 5 flips equals 1 minus the probability of no heads on 5 flips. And then we can transition from this into single coin flips using the logic from this bullet point. All right, and so rather than write this 5 times, I just put a 5th power. So hopefully that's okay. And then we can go through and just write it out. So get 1 minus, and then probability of not getting heads on a coin flip is a half, and then a half again, then a half again, then a half again, then a half again. Again, these are because these are independent, right? So that independent part is important. So since each coin flip is independent, we can go through and just figure out what the probability is for 1 coin flip and then just repeat it 5 times. And then we go through and we do the math. And so we get 31 out of 32. So it is highly likely if you flip a coin 5 times, then you're going to get at least 1 heads. Okay, let's look at a homework example. According to a recent study, 64% of households from a certain large region no longer have landlines and instead only have cell phones. Suppose 3 households from the region are selected at random. What is the probability that all 3 have only cell phone service? And then what is the probability that at least one has only cell phone service? Oops. There's 2 slides in there that are the same. Okay. What is the probability that all 3 have only cell phone service? Okay, so that's simple enough to calculate. You just go through and you just find the probability that 1 has cell phone service, which was 64%, right? So yeah, 64%. And then you just do that 3 times. If all 3 have to have cell phone service, then the probability that 1 has cell phone, the probability that another has cell phone, the probability that another has cell phone, and that gets you your result. Oh, and I skipped over this because I was in such a rush, but the important thing here is that the events are independent. Okay, if you had a really small region, like if you were only looking at cell phone data for, for 30 people or something like that, and you were doing this same probability example, then there's a strong argument that the results are associated at that point, and that going through and pulling out one of the people who have cell phones would affect the probability that's for the rest. Okay, but when you're dealing with a large region, in the thousands of people or tens of thousands of people, then typically we go through and ignore, the effect that one person would have on the rest of the data because it's going to be so small. Okay, and so the reason that we can go through and transition from the probability that all 3 have cells to just multiplying the probability that of each one individually having a cell, that is because of the fact because they're independent. And one other thing here just occurred to me while I'm looking at this slide. What this is I didn't write this, but maybe I should have. So what this is this is the probability that the first has a cell phone and the second has a cell phone and the third has a cell phone. So that's the connection here. If you're like wondering how we got from and over to these examples. And the same thing is true on the previous case. So if you're going through and finding the probability, if we go back here I guess these do have and in them. I guess where I did switch was over here. Okay. I'm making a mess of this presentation. All right. So anyway, all 3 have a cell is the same thing as 1 has a cell and 1 has a cell and 1 has a cell. And since they're independent, you can go through and multiply by the probability of each individually. All right. And then question B, what is the probability that at least 1 has only cell phone service? And then there we want to go through and use the complement. The probability of at least 1 having a cell is equal to 1 minus the probability that none have a cell. And to go through and find the probability that none have a cell, that's the same thing as the first one doesn't have a cell, and the second one doesn't have a cell, and the third one doesn't have a cell, and each one of those is 0.36, right? So if it's 64% chance that you have a cell, then it's 36% chance that you don't. Right. And so that's why we're multiplying by 0.36 here, is because now we're looking for the chance that you don't have a cell. And so there's going to be 3 of those. There's 3 of those ands that's embedded in here. First one doesn't have a cell. Second one doesn't have a cell. Third one doesn't have a cell. So that's why we've got this third power is because we're dealing with 3 people and each one does not have a cell. And then we go through and we take 1 minus that to get our probability. Okay, so I made a little bit of a mess there, but I'm not going to re-record it. All right. And then let's see. Is that it? Yep, that is it. That's it for the presentation. Thank you for watching, and I'll see you next time. Bye-bye.